Okay, I think we'll get started. Remember the homework. The last homework is due by the end of today. And okay, so today's topic is visualization. Basically, just going to be making, running through how to make plots in Python. Basically, just going to be a bunch of examples. And also show you how to make animations at the end. Okay, so what we'll be using for this is called Matplotlib. We've already seen a little bit of it in the previous lectures. This is the standard scientific plotting package for Python. And it's, as you can tell from the name, it's sort of designed to mimic MATLAB plotting, if you're familiar with that. It's not an exact clone, but it has a lot of similarities. You can basically do everything you want. And because of that, it tends to be a bit sprawling. It's sort of, it can be a bit, sometimes a little hard to figure out how you want to do something, but it's all the functionality is there, just requires a little digging to find it. Okay, we'll just start off with just a little caveat. It can sometimes be a little surprising when you get started with it, because sometimes you'll do something and it won't show a plot. Right? You'll try to make a plot and nothing will happen. And that's because Matplotlib tries to make a distinction between interactive plotting and plotting in scripts. So for instance, if you're working, in IPython, and you call plot, yeah, you want an X window to pop up with an image of your plot in it. But if you're writing a little script to make a plot for a paper, you don't want that window to pop up, right? If you're just writing a file, if you're just writing a plot to a file, you don't want a window to pop up on your screen. And so Matplotlib tries to be clever about that and decide when you're doing what. So normally, if you just type Python and use Matplotlib, it won't show anything until you actually tell it to show you something. So basically, in normal Python, you'll be in essentially script mode. So basically, it won't show anything until you call until you call this Subplot Function show. And when you call this function, then it will block. So it'll pop up a window, and then it'll block until you dismiss the window. So it's basically, I want to show the plot, I want to interact with the plot, and then I can't do anything more in this terminal until I dismiss the plot. IPython, by default, has the same behavior. But if you pass it the --pylab option, then it will behave more interactively. So now if you make a plot, it'll just pop up. It'll just pop up right away, and you won't have to dismiss it to keep working. Okay. So just a little caveat. So let's make a plot. Now we've seen, this is a little bit of a review because we've made plots before. Okay, so we're going to import NumPy and then this pyplot package. Make some linear spaced x data. Call sign, plot it, and you notice this MATLAB style string here. Just a star character means plot stars. Now, I want to adjust the plot, so I can call this xlim function to change the x limits. So before they were auto-determined, now I'm going to change them to 0 to 10. Or change them back to 0 to 2 pi. Now I can label the axes with X label, change the font size, add Y label, and title the plot. So all these functions are Pretty straightforward. X label, Y label, title. And you can see that these are global functions. You're not passing any plot option around, so it's obviously, there's some sort of global state, referring to the current plot you're working on that this defaults to. Okay, now if you look at the plot window that's popped up, you'll see these buttons either on the bottom or the top. And what do these buttons do? So I'll start with the middle one here. This one, the cross. This you can grab the data and move it around. So interactively explore the plot. Here you can zoom in. You can adjust some of the spacing and parameters of the plot with this sort of those 4 arrow button, and save the figure with the last one. Okay, and then now the first 3 buttons. Basically, whenever you do these operations, you can then now, if you change your mind, you can undo them or redo them using these options. So that's undo, that's redo, and this one home means just go back to the start. Just clear all the futzing, fuss around the plot, and it's like, I made a mistake. Just get rid of all that. That's the home button. But the first 3 buttons won't do any, when you just pop up the plot, they won't do anything because they only handle the interactive stuff you've done. If you modify the plot through the command line, they won't. These buttons don't affect that. Okay, so that's one basic plot. So I had my window, and I want to clear it. So clear figure, CLF. I'll start making subplots. So there's the subplot function. It takes 3 arguments. First 2 arguments are how many rows and columns I want of plots. And then the last argument is then which one of those plots I want to work on. Which one of those subplots I want to work on. So here, we didn't need this. We're making one row. We're making a grid of 1 by 1 plots. So this is just one plot. Doesn't really do anything. But here I'm going to say now I want 2 rows, 1 column, and work on the first figure. And likewise, 1 row, 2 columns, work on the first figure. 2 by 2, first figure. And now let's start adding data to this plot, right? So so there's now 4 options here. So this is now set the global pointer to I'm going to work in this plot. So now if I have call plot commands, it'll go into that subplot. Okay. And again, V is the style for a little upside down triangle. Okay, so now I want to work on a different subplot here. So 2, 2, 4. So the 4th subplot in this grid. Add some data to this. Now again, you can use multiple style characters in the little string. So RP, R is for red, and P is for pentagon. Okay, now I want to start working on the original subpanel. So I just call subplot 221 again. And now plot will then re-add, add data to that plot. And again, so an MD, magenta diamond. Okay, now move to the third panel. So you can see they're numbered going left to right and then down, right? So 1, 2, 3, 4. Does that make sense? Pretty straightforward. Okay, so this is science. Most of our stuff's going to have error bars. So let's start doing that. So again, make some fake data, plot it. S, here the style character S is for square. I'll explain so I'm going to add this label keyword to option 2. I'll explain that in a little bit. Okay, so now error bars. So their error bar function, X and Y, the centers, the points where I want to plot the error bars. Y error equals 5, so now this says give me an error bar plus minus 5 at each point. Usually you'll have different error bars for each point, then you pass Y error equals an array. And if you wanted X error bars, obviously X error. Okay, now that's not great because we can't see the ones in the end, so I'm going to change the X limits. So from a couple of weeks ago, remember the polyfit function for doing, fitting polynomials to data. I'm going to fit a line to the data. Now notice this isn't taking the error bars into account, but in this example, all the error bars are the same, so that doesn't matter. Okay. And now overplot my fit using the polyval function. Okay, you notice I've also added this label thing again. So that, now I can add a legend to the plot. Okay, so I'm just going to say, okay, now make a legend of the plot. And, and log just says, where to put the legend. Here I'm going to say best. I'm not entirely sure how it decides that, but otherwise the options are upper right, upper left, lower right, center, that sort of thing. Okay, so now you can see what the label options are for. There's labeling the data in the plot for use by legend. You can override this by passing strings to legend, but otherwise it will look, if you don't, then it will start looking into the data you added for the labels. Okay? That make sense? Okay, yeah, sorry, this class is just kind of show and tell. We'll clear the plot. So now we're going to do 2D data. So this function is a little tricky to explain. It's easier to just sort of play around with it and figure it out. Basically, it's mesh grid, and it returns 2 arrays. One where it's copied all of the rows. So here I'm giving, so it takes 2 options, an X vector and a Y vector. And now it's going to make 2 2D arrays out of that. One of them with the dimensions of this times this. So if this is M, this is M, so it's going to return n by n matrices. The first with all the values of X repeated. And the second with all the values of Y repeated the other way. Okay, like I said, it's a little tricky it's a little hard to explain. If you just play around through the command line, you'll see what it's doing. Okay, so basically, I just want to make a grid of values with one array being all the X coordinates and the other being all the Y coordinates. Okay, so now I can use those to construct Z, some function over X and Y. And here I'm just going to make a Gaussian. Okay, so these are 2 by 2. These are 2 by 2 matrices. G is going to be another 2 by 2 matrix. Okay, now let's make a contour plot of G. Okay, so you can see it's a Gaussian. It's picked some standard, some standard number of levels automatically. If you can add a color bar with the color bar function. So now I want to So it will pick levels automatically if I don't specify them, but now I want to specify them. So I'm going to make a little vector of 21 equally spaced values between the minimum and the maximum of my z data. Okay, and now just call contour f again with my z matrix and then the value, a vector of the values I want the contours to be displayed at. And add the color bar, but here I also want to customize it, so I can set the format for the labels. I can set how much space is between the color bar and the plot with this pad option. Fraction tells how much of this total width here is taken up by the color bar, and then customize the actual tick values displayed here with ticks. So here I'm just going to say, well, I want a label for every single contour I've got in the plot.
So V means a label for every single contour.
Yes, because it's the same V I used here.
Oh, sorry.
Yeah. So this made this many contours, and then I'm using the same V here, so it's going to be there's going to be one for each contour. So, yeah. Okay. Okay, so we've covered sort of, this is sort of basic, interactive plotting. Now, talk a little bit about more being a little fancier, and and when you're working with the plots in a script, manipulating the objects directly instead of essentially having these global pointers. So basically, the figure function creates a new canvas in a script. It's what you're drawing on. Basically, if you're calling it an IPython, if you're calling it interactively, it'll pop up a new window. And it has its own options for changing the DPI and the size. And this is where you would set, if you want, say, how big this figure is. I want to say this figure is 5 inches by 5 inches. If you're making a PDF figure for a paper or something, this is where you customize that. Right.
Does it return any kind of a handle or something?
Yes, and it returns the figure handle.
So you could flip back and forth between figures to do.
Yeah. There's also it assigns integers to each of the windows, so you can also just pass it the number to flip back and forth. But in a script, yeah, it returns the handle. Okay, again, there's a slight caveat. Again, it's basically the same thing, the same idea I mentioned previously, that it makes a distinction between interactive mode and script mode. And the way it handles that is PyPlot. That PyPlot module is sort of a wrapper for this lower level Matplotlib figure. So PyPlot is sort of wrapping that stuff to do that kind of interactive, to try to figure out whether to automatically show plots or not. So if you're using the low level stuff, you'll typically, it may not do anything unless you actually explicitly show it. So again, just a slight caveat. If you basically, yeah, if stuff's not plotting, try show. Maybe that'll work. I actually noticed that in Canopy it's a little buggy. Even sometimes you do show, it won't do anything unless you actually sort of move the plot around. So anyway. Okay, so now you've got the handle to this canvas figure. So what are the sort of options you do? GCA, get current axes, and in Matplotlib and MATLAB, axes is sort of refers to the plot. Each subplot or each plot is considered sort of the axis. Adding a subplot, this is similar to the subplot function I showed you before. You can set the DPI. You can change the DPI after construction. change the width, and then tweak the subplots, a little to show it to if you want perfectly fine control about where all the edges of the plots are drawn. This is the function. I'll show you that later. Okay, so now let's do 3D. Just a little bit more complicated, but not much. Basically, the real changes here are I'm going to make a figure. Okay, and you see I've now gotten that handle. I'm going to get current axes, and since this is a new figure, it's going to make a new plot. But I'm going to change the projection. So here I'm going to say, okay, I want a 3D plot. Otherwise, this defaults to 2D. So now this ax object is basically my plot. I'm going to say, okay, so now I've created an empty 3D plot. So make some data. This is just x, y, z. Make a little parametric curve. And now, so I've got this ax object. This is my 3D plot. Now I call ax.plot instead of just calling pyplot.plot. All right. So add this data to this specific plot. Okay. And it's a 3D plot. So now I've got x, y, and z, and my label. And again, ax.legend. Similar to what we saw before, just add a legend to this plot. It'll use this label. And then this is, I'll save it to a file. And because it's in a script, if I run this as a script, it won't show anything unless I call plot.show. Now, normally that's what you want. You mostly just want run the script, make the file, and that's it. But if you also then want to see, if you're debugging the script, you also want to see it, then call plot.show. Okay, and that produces this. Any questions about this? Does that make sense? So you're now, instead of working, with the global plot objects, you're now working with the specific plot handles. Okay. And then there was one other thing I didn't mention here, I didn't touch on, which is this Mpl Rc Params Dictionary. And as you probably guessed, this is the dictionary of default style parameters, default options. If you don't specify it, this is what default gets used. So here I'm going to change the font size of the legend to 10. That's this thing. So instead of, I could have also just, called this function with font size equals 10. That would be equivalent.
When you set it with Mpl Rc Params, does that affect every single figure that you will subsequently make?
It'll affect every single, let's say if this is a script, it'll affect every subsequent figure in the script. Got it. Yeah, but it won't save to disk, right? But yeah, in this Python instance, it'll affect all subsequent figures. Yeah. Okay, I think I went through all this. But yeah, it just sets the default parameters in that Python session. Okay, you guys probably all know this, but just to reiterate, make suggestions for making good scientific figures. Obviously, label everything. Add units to everything. Legends. Basically, make it understandable what is in your data, what's in your plot. This might be field specific, but don't put a title label. You typically don't want to add a title label to your plots for talks and papers. Don't use crappy colors. For instance, cyan or yellow, especially on a white background. I will say, yeah, don't save files as PNGs, unless you need it. Always better to save it as like a PDF, because you can always convert that PDF to PNG later. EPS or PDF or vector, what's called vector formats. So they essentially contain the actual drawing commands to make the figure, so you can resize it without sacrificing resolution. Whereas something like PNG or JPEG is just a grid of data, and you can't resize it. And most of the time, you'll want to write scripts to make your plots, because if you can't reproduce a plot, it's almost useless, right? Okay. So now let's just do something, make a plot for publication. Okay. So I'm going to use the fancier interface, making a figure. So again, I'm going to set the fixed size here. Units default to inches. So this would be 3.375 inches by 2 inches. And DPI 600 dots per inch. Okay, make a subplot. There's just one plot in this figure. Plot the data. So here you notice I said, so colon, make it a dotted plot, make it a dotted line. Color equals K. K in printing refers to the key color, so it's black. I could have also just done K colon here instead of having this color equals K option. Okay, now before I showed, you can set defaults to the RC parameters, but if I want to individually, let's say I want to individually manipulate these tick labels, I could do something like this. So here I'm going to say for t in A is my plot, that axis object, the y-axis, and then get all the major ticks. So get all these major tick objects. And then for each one of them, I'm going to set the label. For each one of them, the object is sort of this line, the value, and the position. So for each one of these, I'm going to say set the font size. So in this example, I'm setting all the font sizes to 6. So this is it's kind of the hard way to do it. But if you did want to customize individual labels, this would be the way to do it. Okay. So all this does is basically just change the font size of the Y labels, the Y tick labels. Okay. So I'm just basically shrinking all the Y labels. And likewise for the x-axis, just replacing y-axis with x-axis. Okay, so now what I want to do is now I'm not, I'm incredibly OCD. I want to slightly adjust this rectangle. And you do that with the Subplots Adjust command. And these units are relative to the size. So the units go from 0 to 1. So this is 0, that's 1, 0, 1. So basically just saying what's the position in this relative coordinate system of this line, that line, that line, that line. Okay. And you can see, yeah, that's just a very minor tweak. Okay, adjust the x limits, add a y label. Now, is everybody familiar with tech? Is anyone not familiar with tech? Okay, so tech is a scientific formatting package, and it comes with is what's called tech math notation. So I'm going to set this y label to this. You notice I've got this dollar signs around this /omega_1. So this stuff in dollar signs is this tech math notation. So it switches modes and says, okay, the stuff in here is an equation. And what the equation says is I want the Greek capital letter omega and then _1. Oh, sorry, subscript, thank you. Subscript 1. Okay.
You might want to talk about what the R in front means.
Yes, that was the next thing. So R in Python means this is a raw string. So normally in Python, if you have these this / character, it'll escape the next character. So for instance, you put in \n, that's a new line, right? So what the R just does, it says to Python, I don't want that. Just give me the raw string I typed in. Otherwise, it will just convert this to, if you drop the R, it will just essentially delete the slash, because /O will just be O. Okay, so now if I look at that, it's hard to see, but now I've got this label here, yeah, Greek omega subscript 1. So yeah, so tech is just a nice way of writing down math notation in ASCII. Okay. So yeah, if you're trying to do something in dollars and it doesn't work, this is why. You can just do a \$ if you just want a raw $. Okay, likewise, X label, omega 2. Oh, sorry. You notice, so this I did with Y label. But now I'm just going to write some text. So I could have done this with X label. Should have done this with X label. But for the purposes of this class, I'm going to do it with text. So this is just saying I want to write this string at this position, XY position on the plot. And you notice the units here are in data coordinates, right? So this is 163 and minus, off the bottom of the plot, so minus 180. Okay, use the same function. Now I want to start, labeling, writing labels into the plot at custom locations. So I'll mark the upper section as stable, and the lower section is unstable. Again, just the same with the text function. And save it to a file. And again, just encourage you to save it as EPS or PDF instead of PNG. Okay, we've got our pretty paper ready for publication. Okay, yeah. Sorry about this class. It's just kind of show and tell. Now we'll do something a little more fancy. Some subplots, some 2D data. Let's see. This is all pretty standard. I'm just gonna. Okay, so now I want to make one subplot. I'm gonna make two panels. So add subplot 1, 2, 1. Work on the first panel. Now here to contour F, before I had 1 or 2 arguments, here I'm going to have 4 arguments. So now I'm going to specify everything. This is the X data, the first argument, this is the X data, this is the Y data, the Z data, and then V, all the values I want contours at. And S has to be a 2D, the third argument has to be a 2D matrix, because that's your contour, your data you're doing contours of. X and Y are either 2D matrices with the same dimensions as Z, or they're 1D just along just along the axis. Okay, and this basically then just controls these, what the data, what the X and Y labels will be. Okay. Add some labels. I don't think there's anything I want to. Okay, so I've got this one panel. It's a solid contour map. Now I want to make another contour map, but now I want to tweak the style a bit. So I'm going to have the first half of I'm going to have 22 contours. I'm going to have the first half of them solid lines, and the second half of them dotted lines. Okay. So here's my array of all the contour values I want. Then I'm going to make a style array. Again, first half dashed, second half solid. Okay. And now, so now I'm going to call the contour function. So before I called contour F, that was filled contours. This is now just line contours. My X, Y, and Z data, the values I want the contours at. And then this, I'm going to pass line styles to the styles array. But I want them all to be the same width. So right, so the contour functions, these when you're changing options, either you can pass a single value that applies to all the contours, or an array of values if you want to control the individual contours. Okay, so you see all these contours here are solid, and then the rest dotted. Dashed. Okay, does that make sense? Now you notice that there's no space between the two panels, and you've also got the Y labels for the second panel overlapping the first plot. So first off, the reason why there's no space between the panels is here. So subplots adjust. I said there's these two options: W space and H space, and I set those both to 0. Basically, yeah, the X space between the panels and the Y space between the panels is to 0. Okay. So now, but now I don't want to. You notice they're both the same. The Y labels. So I don't want these. They're messing up the plot. I don't want these Y tick labels. So I'll just set Y tick labels to the empty list. Okay. So that gets rid of the tick labels. Okay. And then just add some X labels. And we're done. Exciting, sexy plot. Okay, does that all make sense? Yeah.
How do you decide which part is dashed, which part is solid?
So that's here. So here's my array of tick values. So the values of the Z data where I want a contour drawn. And then I made an array, a styles array, and this is going to have the same length as my values array. So then it's just going to march through the list. For each value in this one, it'll pick this style. Does that make sense? I made 2 arrays of the same length. One setting the contour value, and the other setting the contour style, line width, line style. Yeah.
Okay.
Okay, so the last thing we'll talk about is how to make animations. Okay, so now I'm going to import this Matplotlib Animation module. I need to tell it what kind of backend I want to use to make the animation. Typical one to use is something called FFmpeg. Make a little dictionary to handle some metadata for my movie. This just will go in the file, but it won't affect the actual look of the file. Okay. So use the backend to create a writer, and here's where I set, yeah, here's the metadata, but also set the FPS, the frames per second, to 15. Right? You're making a movie, you have to tell it how fast to flip the images. And that's this number. Yeah. Television is like 24 frames per second. Oh, sorry, movies are 24 frames per second. Okay. But otherwise, some standard stuff. So I'll make a figure, open an empty plot in the figure, set the X limits, Y limits. Okay, so now there's this sort of with block notation. I'm not sure if we covered, but it basically says execute this block in this context. For the purposes of this class, I wouldn't worry about the details there. But basically, this is just saying I'm going to write. I want to write this file out as my animation.mp4. Okay, and it's going to have 200. It's going to have 200 frames in it. Okay, so now in this block, I just want to make each frame of my movie. So I've got a for loop. Make some X data, make some Y data. I'm plotting it in this plot object that I created up here. Right, so this is the actual plot. So I'm setting the data. Right, so I'm not adding. So if I called plot in here, it would overplot. Remember, every time you call plot, it overplots it on the current plot. Right. This is now saying I don't want to overplot it. I just want to change the plot. Right. So set data. Okay, and then when I'm done, just grab the frame. Yeah, like I said, for the purposes of this class, this sort of stuff is just sort of boilerplate. But you know. Okay, now because you need this FFmpeg backend, it can be a little tricky to run. This isn't installed by default on your Mac, for instance. So here's how you can do it on Signet. Basically, load the Python and FFmpeg modules, and then use this command: xvfb run Python, and then your script. This is the script from the last slide. And this first command is just some X magic. Don't pay attention to it. Okay. And then it will look like this. Okay, remember I was making just random points and plotting them. Okay. Okay, yeah, so this is just what I said before. Yeah, Python it can't create animations on its own. You need some sort of backend. That's what this FFmpeg is for. There's one called mencoder, and they must be installed separately to be able to do this. So if you get errors about this, it's probably because you haven't installed them. Okay, so that's it for the class. Any questions? Yeah.
Can you read data from outside the code?
Yes.
can we?
Oh, you just do it the same. You know, that's actually going to be sort of the homework problem. Yeah, instead of just, for instance, it's here basically where I'm generating the data. It's just random numbers. Just use the data you've read from the file here
Okay.
instead of yeah.
And can we use this animation code to make animation of figures? Like, let's say I have 10 figures and I want to make animation of those figures.
You mean completely different
Completely
figures and just sort of like you're doing like a slideshow or something?
Let's say different materials.
Yeah.
I have different figures of different materials and I want to make an animation of those.
Yeah. Oh, sure. Yeah.
So how to take, I don't know, use those figures which are already there and make an animation.
You mean you've gone through?
Any EPS, PNG,
Oh, okay, yeah. Oh, if you've already got, if you already have those files as those are separate files. Yeah, I wouldn't. Yeah, don't use this.
Okay.
Use there's a there's.
Simple.
We'll send you an email. Yeah, right.
Okay. But in Linux you can do very easily.
Oh yeah, sure, yeah. But there's just a command line program. You can just give it the files and make a movie. Yeah.
So you do not recommend.
No. This is for if you want to actually. This is for generating the stills and the movie at the same time. Yeah.
All right. Thanks.
Okay. So like I said, that's this week's homework problem. Basically, we're going to give you a file called trajectory.nc. That's in netcdf format. Remember that was last week's lecture. And we're going to ask you to make an animation of this data. It's just a set of positions and velocities for particles at different times. Okay, so we'll want the code, we'll want the animation you produced. And we'd also like to see a plot of your own data. You know, use Matplotlib to plot your own data. It can be anything. But just, make a plot on your own and submit it. Like I said, it can be anything you're working on, right? And we'd also like you to, as usual, use version control for writing the code and submit the git log or the HG log with the results. Okay.
Where is trajectory.nc on the website?
It's going to be posted on the
it's not there
in
yet.
the education. No, it's not there yet. Yeah, sorry, I didn't get a chance. So I'll post that after this class. Yeah.
It would just be like a Mercado storage where the lecture slides are.
Yeah, it'll be exactly where the lecture slides are. Yeah, or we might just put a link to like it was in previous year's classes. Okay. So we'll have classes next week and be back to Ramsey's. So you're done with me. Sure.
I don't think it's crucial or anything, but I think it might be worthwhile at some point to mention to people to peruse the Python F8, because we all tend to create our own sort of idiosyncratic conventions for spacing and stuff. I think it's better if people sort of, what's the community practice?
Right.
And then you can make deviations that help you. But
you can only break the rules once you start somewhere.
Yeah.
Yeah, that's not a bad idea.